Welcome back to AP Physics 2 video series. This is Unit 4, Electric Circuits. In Unit 3, we talked a bit about electricity, specifically charge, electrostatics, things like that. Now we're going to be delving into circuits, current, and resistors, capacitors, and putting it all together. And as you can see, we have a lot of equations here. Thankfully, it's not going to be as long of content as Unit 3. This one is going to be a bit shorter, but there's still a lot of equations you should know. So with that in mind, let's just get started. Okay, first of all, let's review what electric charge is. Charge is just a fundamental property of matter. It can be positive, negative, neutral, and it can occur during just a charged object or a neutral object that's polarized. And so we have the conservation of charge that says that charge cannot be created or destroyed and can only be transferred. And we're going to be talking about that transfer of charge in this unit. Another thing we briefly mentioned last time, capacitor. Basically, it's specifically a parallel plate capacitor is a device used to store electrical potential energy. And it has two plates that have an electric field between them. It's a uniform electric field that's between these two plates. And we're going to revisit capacitors in this unit in a different light. And finally, a battery is a device that provides a sustained potential difference. So it just provides a voltage, we call it. Voltage, potential difference mean the same thing. Okay, that was all review. And now going into some new stuff. We talked about charge, but the rate of change of charge is going to be called current. And that's just change in charge over change in time. And you can measure the current through an ammeter that measures, well, the current. And in a simple circuit, the current doesn't change, but we're going to be talking about a few complex circuits in this video, specifically RC circuits that do change their current. Now, speaking of circuits, let's talk about circuits. Circuit is basically a configuration of wires, batteries, and other features that causes charges to move. And usually it looks something like this. This right here is going to be a battery, with the positive terminal being the big side and the negative terminal being the small side. This is a symbol we use for that. Then we can have just a capacitor, which is just these two parallel plates, a resistor, which is this squiggly line. We have not talked about resistors yet, so we'll get into that a bit later. And then, yeah, that is an example of a circuit. So like I said, battery is a device that creates potential difference. And the negative terminal technically pushes the electrons this way, and the positive terminal pulls the electrons. But we talk about conventional current, which says that the protons move. In reality, they don't. Electrons are the ones that move around in the opposite direction, which we kind of talked about before. But conventional current is the direction of positive charges movement, and we just use that. The laws of physics still behave the same, so we just use it like that. That's the battery that creates the potential difference that causes charge to move, but wire actually allows charges to move. And they're usually made with a conductor wrapped in an insulator, like a wire wrapped around with plastic. Another common thing you'll see here is a light bulb, which is usually symbolized like this. And this is a device that uses energy to produce light and heat. And this is actually a type of resistor. Again, we have not talked about resistors yet, so we'll get into that later. But this basically causes heat and light to come out as a result of charges moving through it. And you can use these in circuits to compare the brightness of them and therefore the power dissipated by each of the light bulb. And that we will discuss again later. And like I said, the conventional current or classical current is opposite to the flow of electrons, and that's just because of historical misconceptions by Ben Franklin. Now, we have a few types of arrangements in circuits. Series and parallel. Series are when both components, all charges flow through both components. So let's say I have these two resistors in series. That means that all charges flow through both of them. But I can also have it in parallel, where there's different branches, one resistor here and another here, and not all charges flow through both of them. They split at this branch right here, and some amount of current flows through each of them. Okay, finally we're talking about resistors. Resistance is basically the measure of an object's opposition to the flow of current, and it's symbolized with R, measured in ohms, which have omega as a symbol. Now, the resistivity of an object is just the property of a material that influences the resistance. And so copper has a specific resistivity, iron does, and so on. Think of it like density. It's a property of the material rather than the object itself. And using this resistivity, also symbolized with a rho, just like density, we can multiply it by the length of that wire over the cross-sectional area of that wire, and that's going to be equal to the resistance of that wire. And so these resistors, while wires generally do have some amount of resistance, they're usually negligible. And these resistors have a lot of resistance, and they're designed to be that way so they can have some current going through them. Why does resistance need to be there for current to go through? That's what Ohm's law is. You can find a relationship between the potential difference, current, and resistance in a circuit that basically says the current is equal to the potential difference over the resistance. And so if you have no resistance, you basically have infinite current, which means that's basically not possible. So you need some amount of resistance to actually have a current going through it. So this basically says the current is directly proportional to the potential difference, inversely proportional to the resistance. And so if you have a simple circuit, let's remove the capacitor and the light bulb. This is just a simple circuit right here. You have some amount of resistance R, and you also have a potential difference delta V. You can find the current just using Ohm's law. Now, we can talk about capacitors again. Capacitors, we talked about what they do, but they also have this property, just like resistors, that's called capacitance, resistance capacitance. So it's symbolized with C, measured in farads, again, after another scientist, with the symbol F. Now, capacitance is the ability of charge to move within a capacitor with a given potential difference. And the equation for this one is going to be equal to C is equal to Q over delta V. And so it's the charge on each of those capacitor plates divided by the potential difference. And so if you have more potential difference across them, you can hold more charge. So the capacitance is just a set property of a capacitor, just like resistance is a set property of a resistor, and this is Ohm's law that relates resistance to the current flowing through. This is basically the same thing. It's an analog of Ohm's law. It says that the amount of charge that can be stored on a capacitor has to do with its ability to store charge, which is its capacitance, and the potential difference that's between them. Now, how do you measure its capacitance then? If we have a formula like this for resistance, what about for capacitance? Well, that's just C is equal to kappa, which is just this Greek letter that looks like K, times epsilon naught A over D. You should know what epsilon naught is from the previous video. If you have not watched that, go back and watch it. A is the area of each plate, and D is the distance between them. But what's this kappa here? That's called the dielectric constant. And that we might have briefly talked about in the previous video, but it's basically the value that modifies the permittivity in a certain dielectric. Now, we talked about permittivity before. We talked about vacuum permittivity being epsilon naught. That's where you should remember it from. But if you have another material, not a vacuum, it's going to have a dielectric constant. And a dielectric is just usually going to be an insulator that's placed between the plates of a capacitor. And so this, I think actually in our previous video, one of the MCQ questions mentioned a dielectric. That's just what it is. You put it between the capacitor, and each material has a certain dielectric constant. And so usually it's going to be just 1 because of a vacuum is just 1. And even air is close enough to a vacuum, they can treat it as 1. But if you have something else, kappa is going to be greater than 1. So you can increase its capacitance by changing the material that's within the capacitor. Now, one thing to know is that if you have a capacitor in a circuit, if you disconnect the battery, then the charge has nowhere to go, and so the same charge is there. But that means that when you change its capacitance, for instance, the charge remains constant, but the capacitance, let's say, decreases, then the voltage or potential difference across it also changes. In this case, if capacitance decreases, the potential difference across it increases. So let's say you disconnect the battery, put it in a dielectric. That's going to increase the capacitance, and so the potential difference across it would decrease. Now, let's say you keep it connected to this battery, right? And you change its capacitance. Then the potential difference is constant because the battery always provides a sustained potential difference. You cannot change that. And so the potential difference across the capacitance would be constant. If you increase the capacitance using a dielectric, the charge would also increase because it's directly proportional. So now with that in mind, we can combine some of these. We've talked about one resistor and one capacitor. What if we put multiple resistors together? And so if you put them in series, just like this example right here, the equivalent resistance, we say, of this is going to be equal to, you just add the resistors up. And so you have two resistors in series, just add those two up. The current that flows through them, the equivalent current, is going to be the same. That's because, like I said before, in series, all charge goes through all of them, and so current will be the same. Current is just the change in charge over time. And the potential difference across each of them is going to be different. And you can add up the potential differences across each one, and you're going to get the total potential difference supplied by the battery. Now, if it's parallel, it's going to be kind of the opposite. This R equivalent has a different formula. It's going to be 1 over the R equivalent is equal to 1 over R1 plus 1 over R2 plus dot, dot, dot. And so you just add all the reciprocals of the resistance is up. And then once you get that quantity, you just take the reciprocal of that to get R equivalent. With that in mind, what do we say about the current? Well, as we're going to learn a bit later, the current, when it passes through different branches, stays the same. Well, the total current stays the same, not the individual currents. They are smaller than the total current. And so you can add up the individual currents and you're going to get the total current. And finally, as you might imagine, the potential difference would be the same among all branches of a circuit. And that's because you have the same potential difference that the battery supplies. And so everything in parallel to the battery is going to have the same potential difference. And now, what about capacitors? You can combine multiple capacitors together. They're actually going to have similar relationships with the potential difference or the voltage. It's going to be the same relationships no matter if it's series or parallel. Series, it's going to have this one. Parallel, it's going to have that one. But let's talk about a few other things, namely the capacitance of that and the charge on each plate. And so you're going to have the opposite equations for capacitance. 1 over the capacitance equivalent is equal to 1 over C1 plus 1 over C2 plus dot, dot, dot. This is just the parallel equation for resistors. And so as you might imagine, the equivalent capacitance for parallel capacitors is going to be just the sum of all these capacitances. What about charge, though? Charge is going to be like current. In series, all the charge that's on one dislodges charge from the next capacitor. So if you have capacitors in series like this, all the charge that lands on here and creates a potential difference dislodges the same amount of charge from the other side that moves to the next plate, and it's going to be the same charge throughout. And so just like with current being constant in series, for resistors, the charge is going to be constant for capacitors in in series. And so what about in parallel? It's going to be kind of like current again. So you just add up all the charges and you're going to get the total charge. And so the only thing that's common between them is this potential difference. You cannot really talk about current through a capacitor or charge on a resistor or anything like that. And so always remember these formulas, what they mean, and how to apply them in different ways. Now, we can also talk about the rate of energy dissipation in a current, also known as power, electrical power specifically. Still has the same symbol P, but we have different equations for it. Remember when I said the brightness of a light bulb has to do with its power or its rate of energy dissipation? Yeah, that's how we can find out how bright it is going to be. And so the main formula is I times the potential difference. The current going through a specific light bulb, or to be honest, the current going through anything times the potential difference going through that thing. And you can modify this using Ohm's law and basically write as I squared R or delta V squared over R. And it's going to be the same thing. You can just plug in different values using Ohm's law and you're going to get the same exact equation. They each have their different purposes. This one is especially used for the power dissipation or the power in a resistor because it has the current going through the resistor and the resistance of the resistor. Okay, now we talked about resistors, multiple resistors. We talked about multiple capacitors. Putting it together, we have resistors and capacitors in a single circuit, what's called an RC circuit. Now, I briefly mentioned that before when I said that things are going to get a bit hairy with RC circuits. The current is not going to be constant. We've been dealing with constant current before. Now it's not going to be constant anymore. And so an RC circuit just has both a resistor and a capacitor. And so a simple RC circuit, well, it's really hard to classify it as simple because there are some complicated equations that have to do with this. But this is an example of an RC circuit. So this right here is actually a switch that's going to be pretty common in RC circuits. Because once you close the switch, with the switch, you have the control of the entire thing. You can control when to start the circuit, when to stop it, and so on. And so that has to do a lot with what we're going to talk about in terms of like how things work in an RC circuit. And so this one has two resistors and a capacitor, R1, R2, and C. Immediately after the switch is closed, the capacitor acts like a wire. And a long time after the switch is closed, the capacitor acts like a broken wire. So how does that work in this situation? So if it acts like a wire, that means that there will be current going through both branches. And so maximum current is going to be there. But if it acts like a broken wire, that means that this branch is not going to get any current at all. And so this branch will get all the current. And so there are equations for this. I don't believe you need them for the AP Physics 2 exam. If you're taking AP Physics C, yes, you do need to learn them. But the reason why is because they use differential equations, which is a calculus topic. So yeah, I'm not going to show you the equations, but just know that immediately after, capacitor acts like wire. Long time after, capacitor acts like broken wire. Okay, final two topics. Technically speaking, final two topics, but they actually have a few more topics within them. Kirchhoff's laws. So we have Kirchhoff's loop rule, and that is usually going to be in a simple circuit where the battery provides a certain potential difference, and that potential difference is used by other elements in the circuit. And so you have voltage gains and voltage drops. The voltage gain is when you go through a battery like this one, and you're gaining voltage. You're having a positive potential difference. And a voltage drop is when you're going through a resistor. And that's going to be a decrease in electric potential. And so this voltage drop basically refers to the amount of voltage used by a light bulb or resistor or the internal resistance of a battery or other electrical loads. Internal resistance is just a battery. Sometimes a non-ideal battery has resistance. We usually use lowercase r to show that it's a smaller resistance than an actual resistor. And so what Kirchhoff's loop rule says is that the sum of the voltage drops in each loop is equal to the potential difference of the supply. And so delta Vs, the potential difference of the supply, is equal to the sum of the voltage loads or voltage drops. One way to think of this is this. Let's say you choose any point here, let's say down here, and you just draw a path through the loop in a certain circuit. You go up here, that's a voltage gain because you're going through the battery. And so that's delta V, positive delta V, because you're gaining voltage. Then you go through here, wires have negligible resistance. And then you come down here, which is a voltage drop. And so the voltage of this resistor, the potential difference of this resistor, you have to subtract it because it's a voltage drop. And then wire, and you reach back at the point. And what Kirchhoff's loop rule says is that the sum of this has to be equal to 0. In other words, the potential difference of the battery is equal to the potential difference of the resistor, which we knew already. This is just proving it using a loop rule. Now, one way you can write delta VR is using Ohm's law. If delta V or I is equal to delta V over R, that means delta V is equal to I times R. And so loop rule also says the potential difference of the battery minus the current going through the resistor times the resistor, the resistance of the resistor is going to be equal to 0. Sometimes you see it like that. This is really monumental. You can use it to solve a bunch of circuits. You can even use it in this branch of the complex circuit. Since the loop rule only has a certain loop, you can start here, go through here, down this way, and that is a loop. That is one loop. You can also do the same thing through the other one, and that's why loop rule is really good. You can create multiple loops within a certain circuit, and there doesn't even have to be a battery. You can go through this loop as well. Now, a few miscellaneous topics right here. Resistors can be classified as ohmic or non-ohmic. Ohmic resistors follow Ohm's law. Non-ohmic do not follow Ohm's law. And an example usually is going to be a light bulb because the resistance changes when the current changes. Because in a light bulb, it heats up. And a change in temperature causes a change in the resistivity of a material. Now, usually you're not going to have a formula for calculating the resistivity, but you're usually going to be given a value. But as temperature changes, the resistivity does, which means the resistance changes as well. And so if the resistance changes, that means that the potential difference is going to change. It just is not ohmic, because ohmic resistors have to have constant resistance. Now, like I said about the light bulbs and brightness of light bulbs, it directly corresponds to the power dissipation of light bulbs. And if you have light bulbs in series, it's going to be greater because all the current passes through the series. But if it's in parallel, it'll be less because a partial current would pass through. It breaks up as it goes in parallel. And so if you want to increase the brightness, you want to put it in series. Finally, energy diagrams just show the energy, the change in energy of a circuit. And you can use this to show loop rule because an increase in energy is a energy gain, and then or a voltage gain, and then a voltage drop. And so a circuit like this one, which has a battery here, positive, negative, and then you have a resistor here, another resistor here, and then you have another branch with another resistor. How would you draw the energy diagram of this? Well, you start going up, that's the battery. We're starting at this point going up. Then you go through this resistor, but before that there's some wires, so just some flat space. Then you go through this resistor, which brings it down, but not all the way down, because at this point you're not going to have zero voltage. That's not a complete loop. This is a complete loop. This is a complete loop, but that is not. And so it's not going to be zero voltage at that point. But you are at an intersection point. And so two things can happen. You can either go through this first loop or the second loop. Let's start with the first loop, where there is some wire between and then a resistor. And so you have this flat line and then a resistor. But at this point, it is going to be zero because all you have left is wires. And so this is a complete loop. That means that it's going to be zero voltage once you pass through that resistor. Now, what about this other branch? There's going to be some more wire and then another resistor that brings it down to zero. Because after that, there's only wire in this loop, meaning the loop is complete. And so this is going to be an energy diagram for this circuit. Final topic. We talked about Kirchhoff's loop rule. Now there's also Kirchhoff's junction rule. A junction is just a point in a circuit where wires meet, which means it's usually going to be a point where the circuit breaks into parallel sections. And this allows charges to flow through different paths. Now, Kirchhoff's junction rule basically says that the current entering a junction is equal to the current exiting a junction. That just seems like common sense. But the way he says it is the sum of the current in is equal to the sum of the current out. And so in this example, you have some amount of current going in, you have two different branches that have two different currents, and so it just says that the initial current is equal to the sum of the two currents that go through the two different branches. And then those two combine back to form the initial current once again. It seems like common sense, but it is pretty important. Now, what do these two rules have in common? They both have to do with conservation. The first one is conservation of energy because it's talking about voltage and how it's going to end up at a voltage of zero at the end. It goes through all the voltage gains and drops and ends up at zero, which means voltage is conserved and therefore energy is conserved. Second one, conservation of charge. It basically says that current is constant in here. Basically, you cannot change the current. Again, this is a simple circuit. In RC, you do change the current. And that's where it's kind of like the Wild Wild West over there. You cannot use these. You could if you really like perfected it. But usually you're not going to want to use these two rules in there because at least in AP Physics 2, you're not going to want to use them. Okay. Yeah, and this is just conservation of charge because if current is constant, that means charge has to be conserved. And so generally circuit problems, you can use Ohm's law, Kirchhoff's loop rule, and Kirchhoff's junction rule to do a whole lot with circuit problems. And I do believe some of the practice problems we're going to do have to do with all three of these laws. Okay, time for our practice problems. First is in MC. It says determine the effective capacitance, also known as equivalent capacitance, of the circuit shown. And this is just pretty complicated, but let's first look at these two are in series. So we have our formula for series. It says that 1 over capacitance equivalent, I'm going to call it 3, 4, because it has capacitor 3 and capacitor 4 in it, is going to be equal to 1 over C3 plus 1 over C4. And so that's going to be equal to 1 over 4 plus 1 over 4, because both of these are 4 farads. And when you add them, you're going to get 2 over 4 or 1 half. And so 1 over C34 is equal to 1 half. If you take the reciprocal of both sides, you get C34 is equal to 2 farads. Okay, so this can be replaced with one capacitor that's just 2 farads. Now we have these two in parallel, and in parallel we know that C234, because you're combining 2 and then 3, 4, is just equal to C2 plus C3, 4, which is equal to 8 plus 2, or 10. And so C234 is equal to 10 farads. And so you can erase all this, have just one capacitor that's 10 farads. This is equivalent capacitance. Don't forget this last capacitor though. We have C1234, and this is going to be in series. And so we use the formula 1 over C1234 is equal to 1 over C1 plus 1 over C234. And that's just 1/15 plus 1/10. If you are allowed to use your calculator on this, you can, but you can also just have a common denominator of 30. That means it's 2 plus 3, which is 5 over 30, or 1/6. And so this is going to be equal to 1/6. So C1234 is just equal to 6 farads. And what's the answer choice? That's going to be C right here. Our answer will be C. Okay, the next MCQ practice. The figure at the right shows a circuit with 2 batteries and 3 resistors. Which of the following actions will increase the current through resistor 2? Okay, this looks really complicated. We did not talk about this. But this is just a bunch of Kirchhoff's loop rule and junction rule. We know that this loop is 0 current, or 0 voltage at the end. This loop is also 0 voltage at the end. Those are the only two we care about. There is this, just this loop right here, but that doesn't have R2, and we want R2. And so if you look at the right loop first, you have, you're starting at this bottom point, you're going up, and so V2 is how much you're increasing by, a bunch of wire, then you have R2, and so you're going to minus the current through R2 times R2 is equal to 0. Okay, well that means that current through R2 times R2 is equal to V2, and so the current through 2 is equal to V2 over R2. That is just Ohm's law. We could have used Ohm's law, but you know, better practice with Kirchhoff's loop rule. Which means one way to increase the current could be to increase V2 or decrease R2. Both of those are valid. You can use the other loop as well. You'll find something similar. It's just that V2 is more direct. It directly correlates with that. If you use the loop rule on V1, you have V1, you're starting down here, adding V1, minus I1 R1, because you're going through this, minus I2 R2, minus I3 R3. And that's equal to 0. And so, while it is true that you can increase the current of this by increasing V1, you cannot really prove that easily. Of course, it looks like it is, but you cannot prove it because there are all these other factors involved. You have I1 R1 and I3 R3. Who knows? What if you increase V1? It's going to increase I1 and I3, but not I2. And so there are two answers here that guarantee increasing the current through R2, and so you choose those two, B and C. And now we have our FRQ practice problem about this. This looks like a complicated circuit, but we can break this part into the different problems we have. And so we see that there are only resistors here, so it's pretty much a simple circuit. But in part D, they do introduce a capacitor, and it's like a completely normal circuit problem, and then they just throw in an RC circuit at the end, which is pretty common. Like, you just have one part of one question be about a completely different topic. But let's not complain about that. Let's just get started. What is the current through each resistor? Well, you would normally try to find the equivalent resistance, use the EMF or voltage of the battery, and use Ohm's law to find the current. But in this case, we are not given the voltage of the battery. Instead, we are given this current here, and we can use the fact that within a series, the current is the same, and with parallel, the currents add up to make the total current. And so let's see what the total resistance in each branch of this is. 60 ohms, this is 20 and 40, and in series, resistors add up to make 60 ohms. And this is also 60 ohms, meaning it's really nice. All three of them have the same resistance. And there's basically kind of a rule that current flows through the path of least resistance. That doesn't mean that all the current flows through that path. It just means that more current flows through that path. And using Ohm's law, that means that the amount of current through it is inversely proportional to the resistance of it. And so if all three of them have the same resistance, that means all three of them also have the same current. And so the current through all branches is going to be 0.5 amps. Now, what about this one though? Well, we know that first of all from junction rule, or you can just use the fact that in series they're equal, in parallel they add up to be the same. And these three add up to be 0.5 plus 0.5 plus 0.5, which is 1.5. And so this total current is going to be 1.5 ohms. And the way we would answer this is, let's say this resistor 1, this is 2, 3, 4, and 5. We can say I1 is equal to 1.5 amps. I2 is equal to I3, which is equal to I4, is equal to I5. And all of these is 0.5 amps. Okay, that was part A, not too bad. What about part B? It says the potential difference across each resistor. Okay, that's pretty easy. We know the current, we know the resistance, we just have to find potential difference. That's just Ohm's law 5 different times. And so here we have 10 ohms, 1.5 amps. Ohm's law says that delta V is equal to I times R. And so we just multiply them together. We have delta V1 is equal to 1.5 times 10, or 15 volts. And then delta V2 is actually equal to delta V5, because they both have the same current and the same resistance. And so we can just write that here. You wouldn't do that in FRQ, but we can just do that here. It's going to be 60 times 0.5, or just 30 volts. Okay, and then in this middle section here, you have two different resistances. And so the current will be the same since they're in series. We know that they're both 0.5. So 0.5 times 20 is going to be 10, and 0.5 times 40 is equal to 20 volts. And so that's going to be all the voltages. You can double check your answers by seeing if they follow the rules we know. This is 10, this is 20. We know when two resistors are in series, the potential differences have to add up to be the same. And so that is 30, which is the same as what is in these two branches. And we know potential difference is the same across different branches. Okay, and now part C, it's asking us what the equivalent resistance of this circuit is. So now we do have to calculate that. We know resistances in series add up, in parallel. You have to take the reciprocal of the sum of the reciprocals. And so this is 60, because we found that earlier. And we have 3 in parallel. And so the equivalent resistance is just going to be equal to, 1 over the equivalent resistance is going to be 1 over 60 plus 1 over 60 plus 1 over 60, which is 3 over 60, or 1 over 20. And so the equivalent resistance is going to be 20. But then we also have this here. If this entire thing is 20 and this is 10, you have to add this up because they're in series, and we have a total of 30 ohms. Okay, that's part C. Part D is where we get into RC circuit stuff. And so let's pay a bit of attention to that. It says the rightmost 60 ohm resistor is replaced with the capacitor. So this is now a capacitor. When the capacitor is empty and just beginning to fill, will the current in the leftmost 60 ohm resistor, this one, be greater than, less than, or equal to, greater than, equal to, or less than the 0.5 amps it was before? And, you know, to be honest, they do tell us the answer to one of the previous questions, 0.5 amps. But they won't do that in a real FRQ, but, you know, just don't mind that. We solved it before we saw that, so, you know. Okay, what will it be? Well, before the charge begins to accumulate, immediately after the switch is opened, we know that the capacitor acts like a wire, and it sucks all the current through here, or a bunch of the current. And so this is going to be less, because more current is going through the capacitor than is going through the resistor, because they're in different branches. Okay, when the capacitor is fully charged, okay, now it acts like a broken wire, and so no current is going through this branch, meaning the current is only split through these two branches, and so it's going to be greater because there's more current flowing through each branch now that there's only 2 branches to worry about. So we didn't have to calculate anything there, which is nice. It's just conceptual, just making sure you know what RC circuits are and how they work. And that's it for this video. Unit 4, more about electricity, and this specifically is about current and circuits. Unit 5 next will be our last video about electromagnetism. It's going to be magnetism and electromagnetic induction. So keep a lookout for that.